and view the recording from the website and other past webinar recordings from the website. Please chat your questions as everyone's mics are muted. And then afterwards, if you have a question at the end, we can unmute your mic and you can speak out your question. But if you have a question during the slides or during the demos, just type it over. And if I'm going to get to it, I'll leave it. But if I can answer it right away, I will try to. But yeah, I encourage you to put some questions out. Okay, so you may notice we got a new logo. The old PSim logo is slowly working its way out of the system. I have, so we've got a new logo, so we've got a new brand going on, trying to look a little, flashier for the version 10 release, which is coming in a couple months. So things are getting exciting over here at PSim. So getting going here. So this webinar, we are going to have a quick outline of PSim, so the development company of PSim, and then we'll flip through a couple slides, PSim's functionalities and capabilities, and then we're going to get to some example circuits, and these are mostly based around motor models and motor examples we'll have a look at, but we can sort of look at most things, and I am planning on sort of presenting for as long as my voice holds up, and as long as there's still questions. So nominally set for an hour, but we can easily extend beyond that. I don't really have anything pressing immediately after this webinar. So a quick note, as this is an international webinar, I need to highlight who the particular distributor is for your area. So Europe, Japan, Korea, China, India, Taiwan, Brazil are the specific areas. If not, you're sort of fall under PSim, which is everyone else, which I notice I don't have a slide there for. So I work for PSim. PSim is the development company of PSim. And these are all of our distributors in the various regions. And yeah, as it says at the top there, used in about 70 countries worldwide. What is PSim? So if you're a new PSim user or you're curious as to what PSim is in the webinar, it is a simulation software specifically designed for power electronics, motor drives, and other energy conversion applications. It is positioned in between the very sort of device circuit simulators such as SPICE and the more system control simulators like MATLAB. As it's based upon the ideal switch, but we're bringing in some behavioral models, which I can demonstrate as well today. And these models will be included with version 10, and I have some now that are sub-circuits that you can load into your current version of PSim if you're interested in them. Just send me a message or an email afterwards, or give me a call. You all should have had an email from me directly from my personal email address. Yeah, so PSim, we aim to be a fast simulator. We also aim to be a simulator, like when you hit simulate, that it always will solve and converge and you'll get results. That's the main thing that we try and strive with PSim. Some key features. A lot of people tell us that it's friendly and very easy to use. Our computation engine is very fast and robust. You can simulate control with op-amp equivalent circuits, S-domain blocks, or in the digital domain with Z, the transfer functions. You can put in some C code. There's a runtime compiler. We've got a thermal module for some quick power loss estimations, which is based off data sheets, and it also considers heat effects on the junction. We generate code for hardware implementation. So embedded code generation. I'm actually running another webinar at the end of the month to cover embedded code generation specifically. That webinar is filling up. I would try and get to that one quickly if you're interested in learning how to translate your control schematic from PSim directly into C code that'll just fire away on the DSP. And we also link to some third-party software packages, JMAG, Magnet, MATLAB Simulation. So JMAG is an FEA program for better motor models. and design suites to provide power and control solutions directly from user specifications. So that's outlining the motor control design suite right now. If you're just logging in, there's a couple more people who just logged in. Please chat your questions, and I'll type that out. If you're not sure how to use WebEx, if you float your cursor to the top of the screen that my presentation is on, you should see an option bar at the top there, which gives you an option to do a couple things. But that's at the top there, and just hit the chat and type your questions if you have them. So the PSim simulation environment, everything that you see here, all these different blocks, these are separate modules that are add-on to PSim. So PSim itself is designed for someone doing like a boost PFC or a DC-DC converter, a power supply essentially with analog domain control. So S domain control either through op-amps or some sort of PWM-IC circuit. That's specifically what PSim is for. So you have a magnetics simulation capability, custom magnetics, and then switches and all those sorts of things. As your needs grow, say you need to do loss calculations, so to have an idea of what your heat sinks are, you'll need to add the thermal module. If you want to do digital control, you'll need to add the digital control module. If you want to get into motor drive, you need the motor drive module. If you want to look at, say, solar panels or battery models or wind turbines, you need the renewable energy module. If you want to get into implementation on the DSP directly, you need to get the autocode generations, the sim coder stuff, and then the targets. With the targets, it's actually implements the registers for like the PWM and the ADC for this. But with the autocode, with just basic sim coder, it can just translate into generic C code, so you can implement on a whole host of things. Smart control helps us on the design side of things to design the control loops, so to figure out what the gain should be for your PI controller or your Type 2 or whatever. Down here, if you're going to start looking at VHDL or Verilog implementations, we co-simulate with ModelSim, so you can have everything. Your code, your control code written in ModelSim, and then control a PSim simulation. Yeah, so flipping through these things now, the Pro PSim package, this is a typical circuit that you might see with someone doing with the Pro PSim package. It's a boost PFC based on this PWM-IC here, this UC3854. Here's some waveforms out here. We see that it's working appropriately, and we can see, that there's nothing there's no digital elements here or those sorts of things. So with lots of resistors and capacitors put in, we have an inductor, a transformer up here. If we wanted to, we could just use the basic model from the library or implement one that is more complex. So we can do a custom magnetics model from PSim here. And the internals of this chip have been modeled. So we see that we have all the main IC functions, including undervoltage lockout, IC enable, peak current limit, soft start. These are all modeled, and you can look and probe at all these points. So we can see all the ports for signals coming in and out. Magnetic elements. So here's look at the magnetic elements capability. So we see windings, we have an air gap, we've got leakage, we've got a saturable core. We also have linear cores if you don't need to have that sort of look at the hysteresis effects. And then this is sort of limited by the capabilities of this module are limited by basically your imagination. If you wanted to simulate capacitive coupling between the input and the output, well, this is the magnetics circuit is here. Outside of it is the electrical. You can still add a capacitor from the input to the output if you want. Or if you wanted to have more complex windings over here rather than just 50 turns with 5 milliohms of impedance, you could add an RC network and have fewer windings. So like maybe one winding with an RC network connected in 50 times in series instead of having just one big 50 turn. It's up to you really to figure out what the best way to model your particular system is. Oh, I seem to be skipping a lot of slides. C block. So what does the C block do? Well, basically, you can type in your code. In this case, the example is a sinusoid of x1. So it's looking at the input of on pin 1, and it's outputting that on y. Well, it's doing this sinusoidal transformation to that and outputting it onto y1. You can, and I've got some examples of these. So you can write if statements, loops, define arrays, include libraries that you, if you want to. So we see here we have psim.h, math. All these things are, you can have include whatever you. It's a fully functioning C block. Like basically, you can type whatever you want as long as it compiles. It will run essentially, and it gets executed at every step. The digital control module. So we can see how we're defining the digital world here. So we have a zero-order hold for our sampling, and we define the sampling frequency inside of these blocks. We've got unit delays here to define how the delay is before it comes into the comparator here. We've got some digital PIs right here. So if we wanted to, each one of these zero-order holds operates at its own speed, or defined speed. So you can define them to be all the same thing, or you could define them to be some faster than the others. You could define, for example, these things to work at different. It's all up to you to decide and to determine what is the appropriate speeds for these blocks to work at. And you can see the effects if you define them incorrectly. So you can have speed inner loops and outer loops that work at different speeds, essentially is what I'm trying to say. So we have a conversion tool. So to help you deal with the math to convert an S-domain transfer function into a Z-domain transfer function, you can, in the utilities menu, you just pull up this guy, the S to Z converter, and you type in your S-domain transfer function, and you put in the parameters. You define a sampling frequency. You just state if you want to do this with the Tustin or the backwards Euler, and it then gives you the block diagram that you need to implement with the parameters that you need to input for each one of those things. As we can see here, this is we're doing a PI controller with Tustin, and if we go back one slide, we see that this is in fact the implementation that we needed for that digital PI. Basically, it helps you properly set up that digital logic with the correct parameters. Thermal module. So what does this do? Basically, you pull a device from the database, or you import your own. In this case, we're looking at an Infineon device, a 6-pack IGBT from the library. We have, looks pretty normal. We've got a DC bus being defined here. We have controller inputs along the bottom here. We have the output from the legs on the right-hand side. But up top, we've got 4 additional outputs. And these are defining the switching and conduction losses of the switch and the switching and conduction losses of the diode. This is up here, it's a thermal equivalent circuit. So these ammeters are measuring watts, so actual energy flowing, and then the voltmeters are measuring temperature. So, and then these impedances are watts per degree Celsius, thermal impedances. So you can see the physical representation of what the circuit is showing is that we have a junction of the we've got a junction of the diode and a junction of the IGBT of the switch, and we've got and they're separate. And then we have a thermal impedance from those junctions to another node, which in this case is the case, and the losses from the switching and conduction losses are contributing to the temperature difference between this junction and this junction, or this node and this node, and then we have basically an infinite capacity to dump heat into a 75 degrees Celsius ambient temperature, which is not necessarily a real system, but it does give us an appreciation of what these junction temperatures will be like based on the 75 degrees Celsius ambient temperature. If we wanted this to be a more realistic model, obviously we would have to put in probably a thermal impedance for like the thermal interface, a thermal impedance for the heat sink. Maybe that heat sink needs a capacitance, a thermal capacity. So we'd put in a capacitor into this network here. And then this ambient temperature probably won't stay constant, so we could put a changing heat source out here, voltage source, so an arbitrary waveform, and so we could then look at a more realistic model of this heating up. Basically, again, the model is as good as you decide to make it, and we've seen that this model gives good results. It's within 10% of loss of real losses, and there's been a couple papers published on that front. I can send them to you if you're interested. Just send me an email afterwards. Essentially, though, that this is not doing the job of an FEA program. We're not trying to bite into COMSOL's market share. This is not a multi-physics approach. This is basically trying to give you an appreciation for the kind of losses you need to deal with and what kind of heat sink you need to deal with. This is not going to replace a heat sink modeling program with a temperature gradient across it, all those sorts of things. This is trying to still provide you with a fast simulation, so this does not slow down the simulation in an appreciable way, and that's what we're trying to provide you with. So this junction temperature gets read in by the thermal by the model here, so it gets accounted for. So looking on the next slide, this is a look at the database, but these are some of the curves that have been brought in for an IGBT. So we can see we have different temperature curves been defined, and what the model does is it looks at where it computes what the best approximation is for the losses given the temperature of the junction, and then it uses those and during the simulation, so it updates and then it gives you the loss calculations. This is the look at the renewable energy module. There's a utility tool provided to help you bring in the parameters from a data sheet for your solar model. Pretty self-explanatory. You can also, so here's a look at renewable energy, one of the example circuits. This is with the more detailed solar module, so it has a sunlight intensity and a temperature input, and both can be arbitrary waveforms. And this has an MPPT algorithm with incremental conductance. In the example library, there's a first order differential, the incremental conductance, and a perturb and observe MPPT algorithm that you can use in your own simulations. And you can open these up and look at them once you purchase. So those are available to you. The wind power module. The wind power module the wind model is kind of nice. It abstracts away a lot of the complexity here. So it just takes in wind speed and pitch angle, and it gives you the appropriate outputs based on the model parameters that you put in to start with. And here's a look at a system simulation that with the wind turbine also gives you an idea of the kind of system level stuff that can be implemented with PSim. We have two inverters here. And they both could be operating at completely different speeds or completely different control algorithms if you wanted to, and you can just start growing from here. You adding in complexity and giving yourself as much, starting from a simple simulation all the way up to a more realistic simulation with more parasitic elements added in. The battery models, So this is the curves from this, defining this lithium-ion battery here. And these are the simulated results after these parameters have been put in. The model is decent. The one thing that we are working on implementing is temperature inputs to the model, not currently available. Hopefully in the near future we'll have that available. But we can see that the simulator, the PSim, has given us decent results of the discharge curve. There's a built-in statement of charge measurement for all of our battery models, so you can just stick a voltage probe on that, and you can see what the state SOC will be. But yeah, there's the model is relatively straightforward to use. Getting into smart control. Smart control is a useful program for designing controllers, which can be a bit tiresome sometimes. With this topology, you can do an AC sweep, or you can define it with equations. I'll go quickly into smart control a little bit later. There is a separate smart control webinar happening on Thursday, which I think is almost full. So sign up quickly. But basically, import you get the frequency information somehow into smart control. There's a number of methods, either through AC sweep, import, or equations, or with one of the predefined topologies, and then it gives you an opportunity to interactively choose the phase margin versus cross-frequency characteristic. In this case, this is this is for PFC, and you see we have an inner loop and an outer loop parameter here, and you can move this around, and you see the step response and the bode plots update as you change your frequency, your phase margin versus cross frequency. Here's a look now without that solver in the way. So there's the polar plots. There's some looks at, for some of the, if you use one of their predefined topologies, you can look at what the inductor and the output voltage will look like. You can look at, again, the bode plots, whichever, controller only, closed loop only. You can look at the step response, all these sorts of things, the polar plots. You can also define digital controllers with it. So if you hit calculate the digital compensator, you can define these parameters, and then you can see it'll plot the change here. So with the digital delay, you can see that the phase really takes a turn for the worse at around 10K here. And you can see the similar response on the amplitude. Getting into the motor drive module. So lots of fun things, and again, that's sort of what we're going to focus on, the examples on a little bit later is the motors. Here we see an induction motor being controlled with field oriented control, and it's in the analog domain. And there's slip calculation going on down here, theta, all the various transformation blocks that you need to implement, your ID and IQ control. Here are the various motor drive models that are currently supported. Some of them, and we'll get into some of the differences here. As you can see, there's squirrel cage. There's 1, 2, 3, 4 different versions of the squirrel cage. And I've got an example coming up where I sort of highlight what the difference is between those various motors. And we've also got, basically, we feel it's relatively exhaustive, what we are currently supporting. And if we don't have a model, there's a tutorial on how to build your own model if it's a more sort of boutique model. Getting into the motor control design suite. So doing closing ID, closing IQ, and closing the speed loop can be a bit long-winded sometimes. What we are trying to provide with PSim now is an ability to do all that for you. So with top-level system specifications, you can define, so you take motor parameters, like the inverter switching speed, the max current, all those sorts of things, and you hit generate circuit and it closes those loops for you. So here we can see these are the sorts of things that you need to do to define the controller. So sampling frequency, crossover frequencies that you're looking for, speed reference, and you can define it per unit. And then you just define these things in similar ways, like what the DC bus voltage is, what your motor, so like what LD, LQ are, those sorts of things, what the max current is for the inverter, what's the max power for the motor, and then you hit generate circuit and it closes the loops for you. Actually, the control, this is an older screenshot. Now we've got a much better response for the controller. It just goes straight into it and there's no oscillation. It's straight to set point. And we can see that, so you can edit this. This is the output example. You can edit this now. You can, if you want to put in a multi-level inverter, you could do that. You could change the space vector block, take this out, put it in with yours. If you wanted to implement your own max torque per ampere control, you could put that in. If you whatever you felt like doing is available to you. Say you wanted to run it with alpha beta instead of ABC, you could change that as well. How much? Oh, I've got a question from an individual. How much capability does PSim have for mechanical systems such as inertia? Great question, and I will get that to that at the in the examples. I've got some examples on how to do that. Additionally, I recently released a tutorial video on PSim outlining the mechanical electrical interface block, which I'll also highlight in the demos. So stay tuned, and you'll see an answer to your question coming up. Okay, so the embedded code generation stuff. Just a quick look in here. So this is an embedded code generation ready, and it is essentially the same thing as this algorithm, except for two main differences. Everything in the middle here is the same. The only difference now is that you see these three currents coming in. So zero order holds coming into the ABCDQ transformation. Those are now coming through an ADC, which is defining the physical pin on the DSP that is going to need to look for these particular inputs. So this is now in the way. Otherwise, everything in the middle here is the same. But then on the back end here, there's a PWM block, which is also defining the physical pins of what signals these are going to come out of. Additionally, you can define things like trigger the ADC and whether or not this is going to be like AC coupling or all those sorts of things are going to be available to you when you look inside of these blocks. So here's a look inside the PWM block. So you can define your dead time, sampling frequency, what your carrier wave is going to be, trip zone stuff. All these things are available to you. So, and this is PSim will then, so you select here what you want to do, and then PSim generates that code. And so basically, as long as it's simulated, and as long as the hardware matches the simulation, everything should work when you generate the code. We also support the TI-DMC library. So these are some of the blocks, and all the various versions are available. Here's a look at sort of the complexity that can be implemented. So inside of the sub-circuit, again, we see an ADC defining the inputs to the DSP, and then some PWM and a digital out defining the outputs from the DSP. So inside of here, this is what's going to be code gen, and a relatively complex circuit. In this case, it's PMSM controller, sensorless control. And this is actually the low voltage development board from TI. So we're actually starting to get into modeling all of the TI dev kits. In this case, we have, and I'll get to those in a moment, but one of the other great functionalities of the embedded code gen system is that it'll set up the SCI interface for you so that you can pass variables back from the DSP while it's running to PSim, and then you can plot them on our little oscilloscope utility. You can also change variables with it. So you can be, in this case, you can change, you can update these parameters in the DSP's memory while it's running, and you can also look at these parameters while it's running. It's a fun little, there's a couple of tutorial videos on YouTube on this one. And this, okay, so here are the dev kits. So in TI's control suites, they have application nodes, application circuits for PMSM, BLDC, and the induction motor, and sensorless and censored and sensorless control. Try and say that 3 times fast. They also have a TI, a high voltage, it's called the high voltage motor control plus PFC development kit. And that's been modeled in PSim, along with all of those app notes, so that you can then implement those with PSim. Here's a look at the setup. So here's the dev kit, and this is the PMSM motor that they supply, and you can see it's running away. And look on the oscilloscope there. So here's a look at some of the schematics. So this is the dev kit up here, and down here we have this is for the sensorless field-oriented control of the PMSM. What we've done is you can implement this with either the F28335, which is the floating point DSP, or you can use the 28035, which is the fixed point DSP. So whereas with the app notes, I think some of them are only for one or the other. We've got them for both. So you can do sensorless or censored control for the PMSM. So here's another look at the simulations. BLDC, so this is trapezoidal control. This is sensorless, censored, and then the induction machine, censored, sensorless. Oh, I don't have that last one, but it's all there, and it's either fixed point or floating point. There's some pages on the website that you can look at for that one. Okay, so MAG coupler. This is co-simulation with JMAG. So instead of using our motor model, you can replace that with a more realistic FEA, like multi-physics model from JMAG. Now, there's 2 versions of this. One of them, PSim and JMAG need to converge at every single simulation step, which might take a little while. So I wouldn't recommend you use it right away, but maybe after you've designed the program, you can run it overnight, because the multi-physics program will need to converge, and that is sometimes not a trivial task. Or you can pre-compile into basically a really big lookup table, and then PSim will handle that. So then it runs at regular speed. So then you can do a much more realistic simulation of your models than what the native PSim models can provide, which is still pretty good. Then co-simulation with MATLAB Simulink, pretty self-explanatory. The PSim power circuit, if you wanted to, will just show up as a block in Simulink. You can actually put as much as you want into PSim, and we're really starting to implement. There's most of what you would want to simulate in Simulink is now simulatable with PSim. So you can maybe start getting away from having to use MATLAB and do all of it in PSim now. This is another interesting module for co-simulation with Verilog and VHDL. So you can define and model sim your code, and then PSim will run it. So PSim will run the power stage, then you can make sure that your FPGA code works appropriately. Next thing up, so PSim, so we're about to get into the examples. So dedicated for power electronics, there's PSim was specifically designed for power electronics. The founder developed PSim because he was getting a little bit sick and tired of trying to do power electronics simulation with the existing platforms that were available to him. Everyone says that it's easy to use, and we're really starting to add more and more interesting functionality. Okay, so I'm going to get open PSim here. Let's pull up PSim. And I will get some, okay, October, okay, first things first, motor models. Okay, so we've got 3 motor models here. These are induction machines. So squirrel cage induction, and then we've got another one. I've got a little thing that says shared here, so I can actually read what the actual title says. So we've got squirrel cage induction, which is the top one. The next one down has the neutral, and then the next one down is linear, and then there's no linear one. These have the same outputs here. So this is the linear one. If you click on help, it gives you a description of what's going on. Basically, this gives us access to both ends of the wiring, which allows us to do some interesting things. But then let's have just a quick run of these guys and look at the various ways that we can implement a load. And then we'll get into the more interesting simulations as to why these are different. Why is this? Oh, right. Okay. It's, so I'm simulating it, and I'll just pull it up on my other side here. We can see that all of the speeds are the same, and we can also see that all of the torques are the same. So we've got 3 speeds and 3 torques. Unfortunately, the green color showed up on top. I will change that green color into something different so that we can see it, like a darker green, for example. That was not the greatest. Why don't I just take away these? I will take away that one. And I'll take away that one. Okay, so they're all the same. But we've implemented the mechanical load in a different way. So let's look at what's going on here. So this is just a generic mechanical load, constant torque, and here's how we've defined we can define the inertia here. The inertia is defined in kilograms per meter squared. We can also define this load, in this case it's a constant current source. So this mechanical electrical block allows us to define some interesting things here. It converts the speed and torque of the shaft into volts and amps. So to give this an inertia here, we just define a capacitor and attach it to the end here. We could also put in something like a diode, and that would allow us to have a constant current flow, but the shaft speed would be different on either end, because we could put another electrical mechanical block on the other side. And then this is just the same thing as above, but showing how you can use how it all looks the same. So we can also see that I've driven this with labels. So in PSim, you don't have to connect everything up. You can connect things with labels. Another thing to highlight is that wires only join if they've got a dot. So if you decide to start an end of the wire, they'll connect. But if you cross the wire, they won't connect when you're wiring up. And we're using a parameter file to define the various components of these motors. So the parameter file is up here, other parameter file. So you can define here, this is how we've defined it, and then each motor is pulling the same information. So yeah, so each motor has a built-in inertia value. So let's quickly look at my other little fun motor model. Okay, so running sometimes people run motors with abnormal conditions. And let's look at some of those models right now. and how each motor model in PSim reacts. So let's enable the top one here. So with PSim here, we can see there's a resistor. I mean, in the elements menu, it's kind of defined this way. We have RLC branches here. So down at the bottom are some fun nonlinear elements. In the switches menu, there's the basic models here, and then they get a little bit more complicated near the bottom. We have a 3-state MOSFET, and I can actually show you our characteristic MOSFET as well. And we have a, so those are here. Now the thing with the switches is you need to drive them with a gating block, and I'll get to that. The transformers, these are all the built-in transformer models, but if your transformer configuration is in here, the magnetic elements is the next one down, and that gives you the opportunity to actually define that transformer in whichever way you want. So whichever, if it's not what you want, is not here. The other menu is where the op amps are. So there's some ideal ones, and then there's some level 1. So that's got some bandwidth limitations and other parasitic, more realistic effects. Getting into the motor drives. So again, here are all the motors. Here's some built-in current control blocks. And down on mechanical loads and sensors, these are where the other areas are here. So some generic mechanical loads, some gearboxes, some couplings, some torque and speed sensors. But the mechanical electrical interface block is really something that's quite fun. It allows you to build a very complex system and define it in an electrical with electrical components, and then you can convert that back outwards. For example, someone was describing to me a sensor that they were trying to generate, and it was sensing the torque, and it slowed the shaft down, but it didn't actually affect the torque flowing through the element. So there was it sounded to me like it was the equivalent of a diode effect, so a linear relationship, and so we just put 2 mechanical electrical interfaces blocks and a diode in the middle, and that did what they wanted. But let's look at these circuits now. So let's look at the torque. Well, so we've got one side is the neutral model, and the other one is the general model. And let's look at the input currents. So we're doing 10 amps peak to peak, and let's look at what the current, and let's look at what the voltage is across it. Okay, so that looks about the same. Current enters phase A and exits BC, and let's look at what the next one does. So we can see this one, and we look at the speed. So one of them is, the general model is actually showing us that there's some speed increase, but it's to the minus 15. So everything still looks relatively okay. Both models are telling us the same thing, except that the speed is something going on a little bit there, but again, to the minus 15, so not too much really. Let's look at what happens with a somewhat different abnormal condition. Let's look at, so current entering phase A and exiting there. So let's look at the voltage across the, so V line in to in. So let's look at both of those. Okay. This is where we actually start to see something. This M is actually not milli, it's mega. So the symmetrical model is showing us, plus minus 2.5 million volts. So that's actually not true. So we should look at the general model by itself and see what we're seeing. And we're seeing plus minus 6 or 7 volts. So that we can see now that if we start running abnormal conditions, this model is not appropriate. We should be using this one. And we can actually handle, so this situation is a good example of what's going on. And let's look now at the bottom model when we run this in abnormal conditions. So in-phase currents entering, and let's just look at what the voltages look like. I can tell you again that they're going to be different, so let's plot them on different scales. So we're seeing plus minus 7.5 million volts on the symmetrical model, and if we look at the general model, we see a more realistic plus minus 5 volts. So this is a good example of what you need to decide what sort of simulation you're going to be running, and choose the appropriate model from there. Okay, so let's close that down. 10:47. Ooh, I'm running out of time. No. Okay, let's look at some other examples here. I just want to quickly highlight the C block. So this is 2 C blocks. So in the control menu, if we go in here, so function blocks, up at the top here are a whole bunch of ABC and Clark and Park and inverse and whatever, all those various function blocks are here. And then down at the bottom, we have some math function blocks, we have some DLL blocks, and then here's the C block and simplified C block. So I've got some simplified C blocks right now. I'm just going to enable this. I'm using hotkeys, and to set up the hotkeys, you'd options customize keyboard, and then you can define these things here. So I will run this simulation, and so you can see I've defined this count variable 2 different ways, and we can have a look to see what happens. So I define the variable count, and we increment it, and then we display it. And let's look at what happens. So we can see that one count just stays 1 all the time, while the other one actually increments. So the static count is actually counting how many simulation steps we went through. So because this is executing at every simulation step. So what that says is the regular integer is being released every single simulation step, whereas the static int was declared once, and then you can remember all the way through. So that's a good point to highlight. Let's look quickly at this one. If you don't have hotkeys enabled for enable disable, it's the check mark and the X at the top here. So let's have a quick look at what's going on here. So you can see that I've defined some on X1. So the inputs here that we can call are X1, 2, 3, 4, 5, and Y1, and then we can also call T and delta T, so time of the simulation and the time step. So 100 is being declared on X1. So X1, that's going to be the frequency here. So I've got an array defining the frequency, and it's 4 slots. So it's going to, in position 0, 1, 2, and 3, it's going to have 100, 200, 300, and 400 is going to be put in there. Please start thinking about some questions to ask, because we're going to get to those soon. And then in this amplitude array, we're pulling in what's happening X2, X3, and X4 here. So, and then we have another for loop where I build up a sort of a sinusoid, and then we display that on the output. So let's run this simulation, and we can see that the combination of all those things. So we should be seeing an amplitude of 10 for the fundamental, and then an amplitude of 3 for 200, 300, and 400 hertz component. I can't tell that from this particular graph, but we can measure this and okay, look, this looks kind of, I can see some extra frequency components, but what we really should do is run the FFT and have a look at what's going on there. Okay, so let's change the bottom axis into a logarithmic scale. It gives us a little bit better appreciation of what's going on. And then we can also now, down at the bottom here, we can find the global maximum value, which, funnily enough, happens to be at 100 hertz, and it's 10. We can also look for the next maximum value, which happens to be at 200 hertz with a value of 3. What's the difference between the C block and the DLL block? The DLL block is pre-compiled. A DLL file is something that you compile with your compiler, like your external compiler like Borland or Microsoft C whatever, and so you pre-compile it with your own with a third-party compiler, and then you load that, you link that file in PSim. Whereas the C block, the compiler is built into PSim, and the compiler that PSim uses is down here. This software contains an embeddable C, C++ interpreter developed by Soft Integration, so that's that one. So then we can quickly find the various other values here, and we can see that the DSP, that the frequency response that we work. So we managed to find these 3 amplitudes to these 3 frequencies. We can also plot the angle if we wanted to, and we can also overlay EMI standards onto this plot if we wanted to look at what these things would be. But I need to change this first to dB microvolts, and then we can throw on an EMI standard. But I think we're not going at a high enough frequency. Yeah, so we should change this to 40 meg. Okay, yeah. So here's where the EMI standard starts, and we didn't have any frequency components for it to really look at. There's a simulation where you look at this sort of thing. Okay, I've got a question. Do you provide support for embedded code generation for D-Space DSP? Currently, we only support 2 DSPs. The Texas Instruments F28335. So the F28335 or 33X and the F2803X from Texas Instruments. Only those DSPs. And that handles the peripheral definitions. If you just do generic code generation, you will be able to translate a digital control schematic into a general schematic. So let's have a quick look. So I'll run the PMSM. So here we can see all these things that we can look at. So this is the design suite. So we go generate circuit. I need to find a temp folder. So here's a general circuit. So this will get turned into just general C code. You'll have to, if you want to put this on a DSP, you'd have to then define what the PWM timing frequencies and the interrupt routines and all those sorts of things would be. This would just handle the basic translation. We can run this. We can look at things in real time, like a runtime graph of this as it plots, and we can see here's the response as it hits steady state speed. Any other questions as we approach the hour mark? I will continue going along past the hour. I'm going to start talking about smart control pretty quickly here. One thing that I would like to highlight about PSim is there's 2 basic signals in PSim. If you can see, the top level circuit here has red traces. This is a power schematic. And you need to interface between the power schematic and the control schematic, which is defined with green traces, through these current sensing blocks, or with, so this voltage sensor will convert power to control, the current sensor, power to control, and these on-off switches. You need to have an on-off switch controller in front of all of our ideal switches. You don't need to have it in front of a 3-level switch. Or a 3-state switch. So these are you need these to interface. We can see that we've got that this is being driven by a control signal. So you need to have all of those in place. And when it comes to subcircuits, this is a subcircuit down here. Coming for version 10, this will be a little bit easier to deal with, but you can change the picture on the subcircuit. We can edit the image. We can you can draw whatever you want at this point. We could draw, you know, a happy face. Well, look, kind of a really crappy happy face, but so now we see my little picture on it there. You can do whatever so that's one of the things that's available to you there. Also with when you have subcircuits, if you go save in package file, the subcircuits are different circuits, and the parameter file is a separate circuit. All those get clumped together into a zip file when you save as save in package file, everything that you need, and this is a pretty handy feature. Okay, getting to smart control. So I'm just going to change the monitor that I'm sharing. Share this one. Let me move this out of the way. Okay, so there's a couple options. We can define a predefined topology, and the topologies that they have predefined, buck, boost, flyback, forward. In those cases, you can also define with there's a PFC that's available to you. With a single loop, you can do a voltage or current sense is available. Some of the more interesting things that you can use, though, if we launch the initial guy again, is their equation editor. So you can also import frequency response, but the equation editor is actually something pretty interesting. So we can open, in this case, let's open so I'm going to open a more complex file here. Here we go. Open. So this is a cascode, a boost buck. So there's a source converter, which is a boost, and the load for the boost is actually a buck. So we have we've defined at the front end here a load converter, a buck, so we can see the various parameters that define it, some mathematical expressions, and then we see what the compensator is. In this case, it's a type 3, defined with zeros and poles here, and this is the RV is the so we can get the small signal load model here. So we can look at something like the input impedance to it. So down at the bottom there's a return statement. In this case we're returning ZILC, which is the input impedance of that, and so we can compile this and have a look at that. So while it does the thing, it's going to plot us a frequency response from 10 hertz to 10 megahertz, and that'll show up in a moment. There it is. We can also plot something like, so then down near the bottom we have the source converter. So this is a boost converter down at the source. So again, we're defining various parameters here and some characteristic impedances. So we can have a look at all of these impedances as response to frequencies. So we can look at ZOU here, which is the unterminated open loop output impedance of the front end buck. Was it buck at the beginning? The front end boost of the front end buck. So let's look at that ZOU. Instead, let's compile that. So it gives us the opportunity to define whatever we want as the plant in this case. So let's just kind of go with that one. So if you hit OK, it'll come in. So then it'll take us to a new screen, which is, we need to come in now to another screen, which is the, lets us to define the sensor. So in this case, it's just a resistor divider. So we can have a look at what the frequency response of a resistor divider is, which hopefully will be a flat amplitude and phase response. If it's not flat, there's going to be something incredibly wrong, but in this case it is flat. But say we're actually using real devices and there's a capacitor in there, which kind of turns this into a low pass filter. So let's add that capacitance. Let's give it a C of, let's make it something horrendous, like 100 micro. And then let's add that into our resistor here. So 1 plus S. So we just call the S variable as the low pass variable, and C, everything is case sensitive. And then if we compile this, we should see a low pass response. So we've added in that basically turned it into a low pass filter. So we can roll forward with this one. Hit compile. And this will take that as the sensor, and then it gives us the next thing we can look at is to define this now as it gives us an opportunity. Oh, I hit compile, hit OK. Is we can move that now into our sensor, and then we go and get to define what kind of controller we want to use. So it's just giving a thinking. I don't know if you can see my cursor flickering, and then so now we can choose what we want to run here. So let's go with PI. Okay, that's really interesting. really interesting. I'm not sure exactly what's going to happen here. Obviously, I chose a very odd plant. I think it was a parameter that wasn't supposed to be used as a plant. But we can you can cruise around here. I'm actually going to exit out of that one. That's not a very good example to choose. Let's just look at something simple in this case. Let's look at a buck, voltage mode control, sensor, and let's look at this guy with the type 3. To cancel, let's actually cancel. Let's run this with a voltage divider. Okay, type 3, okay, set. Okay. So now we can look around at this and what the frequency response is. Okay, questions. Please ask questions at this time. Anyone? Have a look at, here's how you do the digital compensator. Now we can display the digital graph here, so we see on the bottom line here and how that changes as you move around. Say, for example, we only ran with 6 bits. We can see how that changes things, and we see how the phase really gets affected by running with 6 bits instead of 12. 12. Let's add in a whole bunch of delay if we wanted to. This really starts affecting the phase. Anyone? Questions, please. Anyone at all? Okay, maybe I'll keep going through with share my desktop. Let's switch monitors and go back to the PSim monitor. Save changes, no, I don't want to save changes. No, I don't save changes. Let's have a look at I wanted to show the characteristic models. No, I don't want to save changes there. I will move that. Let's have a look at, okay, AC sweeps is one thing to highlight. So this is how you set up an AC sweep. So the key thing to note with the AC sweep block is that the source that you're inputting to perturb the name has to match. So name has to match this name. And then you choose the start and amplitude. There's a video on YouTube to help guide you through this process, and then some frequencies for extra points. So when you simulate, what's going to happen is it's going to basically the parameter block here will take over this source and will run 25 simulations, the number of points there plus these extra points, and will run all those simulations, and then you end up with a frequency response. And then you can import this into Smart Control and go from there if you want to. The next thing you need to look at, so that's running an AC sweep. So the AC sweep probe is ground referenced. It's important to note, so it's always referenced to ground. If you want to reference on like a flyback, you should use the voltage sensor, because the isolated voltage sensor, and put the probe on the other end here, because this will then give you a output relative to ground. Let's have a quick look at the test buck, this guy. Okay, this is a buck converter with our behavioral model. If you aren't familiar with our behavioral models, I wouldn't be surprised because they are new. They will get added to version 10. So I'm just simulating this buck right now, and we can have a look at VDS, for example. So in a regular PSim simulation, this switch is ideal, which means that you don't see this transient response. So now you can add these models in, and it's datasheet driven. So you can the things that you can define this model with are defined here, and we're driving it in this case with a plus minus 10 volt source. Let's redraw and add now on a different screen the current flowing through the gate resistor. Let's look at that. So there's the current that we're driving the gate with. Again, pretty interesting stuff. So you'll notice that it doesn't have the very high frequency characteristic, which we've not included in the model. So if you want to have that high frequency ringing, again, this is not. We didn't feel that it was really pertinent information. So to avoid trying to, once you start adding that really high frequency stuff, the simulations start to slow down quite a bit. Whereas if you can sort of abstract that away, you're still going to have a very fast simulation speed. So again, let's redraw and add, maybe let's look at the current through iDrain. Maybe iDrain, is that something interesting? Yeah, we can see something going on down there. Yeah, so these are new. If you are interested in this model, please message me. Otherwise, you'll just have to look for it in version 10. The next thing I'd like to look at here, test out. So we have a reverse recovery model diode. So here's the parameters for the reverse recovery of this. Let's run this and have a look at it. Here's some of the parameters for that reverse recovery diode. So it's an on semiconductors diode. Let's look at the diode, the current through it. Again, you can see that we don't have that high frequency ring, and so it gives you the peak value, but it's not giving you the sort of noisy information. So this is now available. If you want these models, please email me. or they will just be included with version 10. What else can I talk about? Transformer with parasitics. Here's the example of that model I was talking about earlier. So here we have 10, so a 30-turn primary defined with almost no winding resistance, but the resistance here is now in this RC network. So we can look at parasitic capacitance, ringings types there, input to output parasitic capacitance, and we can push this down into a sub-circuit if we feel like. So just highlight everything, right-click, and then create sub-circuit, MB, and then this is TX sub. Just give it a name, and then it just pops down. Fun. Okay, well, I mean, I'm sort of losing my voice and I'm running out of things to chat about, and there's no other questions coming through right now. This is sort of your last chance. Otherwise, coming up at the end of the week is I'm doing the same tutorial tomorrow again. Thursday, I'm running a smart control tutorial, and then at the end of the month, we're talking about embedded cogeneration. Okay, so that's it for this session. Thank you so much for attending. I hope you find it interesting or found it interesting. You will have access to the WebEx recording on the WebEx server, but we're going to delete that within a week, and I'll send out a link with the exact location on the website where you will be able to look at the recording at your leisure. Thanks again for attending, and have a good day.